All right, let's get going. So, day 3, asymptotic analysis. We'll get into what that means in a second. What questions do you have before we get going? Anything so far? The labs were Monday and Tuesday. Raise your hand if you didn't go to a lab. Did you email me? OK. If you haven't emailed me and you haven't gone to a lab yet, you're delinquent. So make sure you let me know. I hope the lab was OK, all things considered, except for the person I gave bad gouge to and went to the wrong lab day and didn't see a lab TA. Everybody else is all right? That was my fault. Hi. I'm sorry? Oh, yeah, come on in.
Sorry, I got the wrong location.
OK, names?
John Kenny.
John, give me 1 second.
Yeah.
With the labs, so hopefully it was fairly straightforward. Hopefully you provided something, and if it wasn't perfect, then not a big worry. I mean, the big deal is to work on the lab in lab, get something done, and ask some questions and so forth. I mean, we'd love it if you could get the lab actually completed. That's great. But if you can't, well, we're not going to like stress too much about that. OK. The other thing about lab was what? I forget. I'll think about it. Any questions about the lab itself? No? Yes.
How many
Ethan.
labs will you be seeing?
Oh, I'm just TAing one lab actually at this point. Is it yours? It is your lab. Yes. I was there yesterday, as were you. Oh, I know. That's what I was going to say about TAing. I tried to get to all the labs. The one that I didn't get to was the 4:30 p.m. lab yesterday. Sorry if I missed your lab. I had another class to teach. I'll try to get in there at some point or another, just to say hi and introduce myself and like in person and say hi. That's that. OK. So before we actually get going with the lesson, we have John here, who is going to talk about the Tufts Mentors program, engineering mentors, I guess it is. And the Tufts Engineering Mentors is not specifically not strictly for engineers, which he'll talk about, unless something changed since 1:30 today. No. And I think if you are interested in having somebody that you can go to talk to about, hey, what's my Tufts path going to be like? Somebody who's already done it before. This is the guy you want to keep in touch with, and go to the website or the Facebook page and talk to him about that. If you happen to be a junior or a senior, I'm stealing your thunder a little bit. If you happen to be a junior and a senior, you can be a mentor, which is kind of fun too. So over to you, John.
Yeah. So he kind of introduced me. So Tufts Engineering Mentors, we're a program that pairs upperclassmen students with underclassmen students within your major. In addition to giving you advice on classes and things like that, it's just someone that you can reach out to at any time. Send them a text, an email, a phone call with any type of question you might have. So in addition to this academic stuff, you might have difficult questions about anything from where to go for late night food, or maybe dealing with difficult questions that you don't feel comfortable asking your advisor. We pair you with a mentor, and they're basically just someone there to give you advice and make sure you're thinking about the right things at the right time. So you should be thinking about internships now. You should be thinking about maybe doing a senior thesis. What things that may be a year and a half in advance that you may not be thinking about, but you need to start preparing for now. In addition to that, we host events that have workshops, different networking opportunities. We have direct relationships with many different businesses that offer us job opportunities. We share those with all of our members. And there's a lot of cool stuff that we're getting involved in this semester. So I'm going to hand out a survey. We'll reach out to you guys with email with a little more information. And next week, we're going to be having our what we call mentor speed dating, which is where you spend time with all of the mentors, get a feel for someone that shares the same interests as you and can be really helpful to you. So I'm going to hand out the surveys. Just write down your information, and we'll be contacting you within the week. And
you don't have to actually date your mentor. The speed dating is not about that. John, do you happen to know the Facebook page?
If you search Tufts Engineering Mentor, it should be facebook.com/Tufts Engineering Mentors.
Facebook.com/Tufts Engineering Mentors should do it. OK. Are you going to want to collect these now or at the end of class?
Yeah, if you want to just hand them all to this side, I'll just come up the alleyway after. Yeah, if you already filled it out in another class, then you're good to go.
All right. You guys need to learn a better algorithm for passing out pieces of paper. No, you need to just pass as many behind you as you can. Just keep passing to anybody who doesn't have one, and you will all get it much quicker. Trust me. That's the way it goes. Don't do it in a lot. Actually, this is actually perfect for today's class. If you pass it 1 to 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 1, how many people does that have to go through? Everyone, right? If you take one and you pass it to 2 people behind you, and he passes it to 2 people behind him, and she passes 2 people behind her, et cetera, you go much, much faster. That's actually a parallel algorithm, but much faster. Yes.
So then the other people in the front row don't get
No.
it.
The person. So you pass it. Okay. So you pass it sideways and backwards, but that's the way it works best. All right. Let's see. When you get done with the little form, John, do you mind sitting in, being in the back and collecting at the end, in the back here? Okay.
Yeah.
Just when you're done, just pass them back. When you're done filling it out, okay, just pass it all the way back. Okay. All right. While you're doing that, anything else, John?
No, that's it. We'll contact you via email. Check us out on Facebook.
Okay. All right. Thank you very much. So back to class today. So here's what we're going to do. Relatively straightforward class today. I'm going to show you the Unix tip of the day, and then the Eclipse tip of the day is actually going to be on debugging. So if you do use Eclipse, then there's a built-in debugger. I mentioned it on the first day, and then you saw it if you looked at the little video 0, or the video for homework 0, then you saw a little bit. But I wanted to go through a little bit more details about that. Now, if you don't want to use the Eclipse debugger, you can feel free to use any other debugger you want. In the background, Eclipse uses, I believe it's the GDB debugger, which is a command line debugger, and it does it for you. But it actually makes it really easy to see what's happening in your program without you having to do anything special. So I'll show you that. And then we're going to introduce this asymptotic analysis, which is really the way that we put together or that we analyze programs to compare them, to analyze algorithms and all that stuff I was talking about last week. Something like that. Any last call on the things?
All right. Anyone else hanging around? All right.
Okay. So that's what we'll do. Questions before we begin on the stuff? Homework going okay? Hopefully. Related to that, tomorrow night, I just did a Piazza post. There's going to be a review session kind of on C++ basics. Like if you're like, I don't really get some of this C++ stuff, come to the review session tomorrow night. Excuse me, 7:30 p.m. And we will, excuse me, get going on that. If you can't make it, it's on the Piazza post. I think it's room 120 in Halligan. And hopefully we'll be able to use that room. Excuse me. As far as, I will videotape it as well. So if you can't go and you really want to watch it, we'll videotape that as well. OK? All right. I think that's about it before we can go into this. The Unix tip of the day. So there's a command. If you don't know what the command you're looking at or you want to use actually does, there's a command called man, which stands for manual, which allows you to get the information for that command. Okay, it describes all the flags that you can use for it, and all the usage and how you use it, and it's pretty straightforward. Some man pages are not written particularly well, but many of them are. Let me show you how that actually works. If I go into the server here, and if I do an ls, one of the commands, right? I showed you this before. ls lists all my files, and they're kind of all over the place, right? The ls command, however, has lots and lots and lots of flags you can use for it. If you type man ls, right, what will come up is this page that says, here's a description of, let me move this back on the screen a little. It looks like it's off the screen. It says, here's a description of the, is that on the screen yet? Almost. There you go. It tells you what the actual command does, and if you go down with the arrow key or the space bar, it gives you all the different options. And look at all the options that that ls has, right? There's like a million of them. It's like practically every letter has its own command, right? The man command tells you how to use all these. And I use a number of them all the time. Like I use the reverse one because I like to see a listing of my files in the reverse order based on time. And the -t flag is a sort by time. So one of the ones that I like to use is ls-alrt. And those are all in the manual command. alrt means give me all the files, including the hidden ones, which start with a period. List them out in a nice format that doesn't just list the program name. Reverse the format, and then give it to me by time. So what it does is, if you look, it says it lists them all out, and it says, looks like the last thing that was updated was my .git config file. I have no idea why. I haven't been using Git, so maybe somebody hacked me. I'm not sure. But it's probably when I log in, it updates it or something. But anyway, the .git config file was modified at 16:39, so 4:39, just like 2 minutes ago, right? And these other ones were modified there too. So you can use that command. And how do you get to those? What that command is? Do a man on it. Okay? Yes. Question. Does not matter. ls dash. Let's see. latr. Same thing. Okay. Yeah. It does not matter what order the flags are in general, and that's generally a Unix thing. As far as if you don't know what command you want, there's another command that's the -k flag to man. And if you do man-k, that I think it actually stands for context. And what it does, it looks through the manual pages and says, oh, this manual page talks about this. So you can do that. So if you type man-k copy, which is not a very good example because there's like a zillion things, right? Then you'll be able to find out what commands have copying ability of some sort or another. Okay, but man-k is a good one. And by the way, if you're in the man command, and you want to get out of it, you just type Q, and it puts you right back onto the terminal. Okay? Other questions on that? One of my friends was, when she was in grad school, she used the man command a lot, but for whatever reason, she got it through her head that she could use that command on Google. And it actually works relatively well when you type man and then a command on Google, because Google just searches, and it's going to probably find the page you're looking for. But she wanted to look up the absolute value function. And so she types man abs, right? And she got a completely different list of things than what she was looking for. She did not get what she wanted. OK. Questions on that? All right. Let's do this. Let me show you. What I'm going to do is log into the server, Eclipse, and hopefully this will come up. And what I'm going to show you is a little bit about how to debug in Eclipse. Okay? So what we're going to look at is the lab from yesterday. How many people, when they were working on the lab yesterday, forgot or just didn't know to check to see that a friend list was null? Yeah, a couple people. I saw a whole bunch, actually. In fact, I saw a couple clever solutions that, as it turns out, didn't need to do that. I don't know that it was the best way to. They handled it in their expand function. I'm not sure it was necessarily the best way to do it, but it actually worked fine, which is kind of cool. But some of you guys forgot to do that or didn't do it for whatever reason. And I have, by the way, I posted the solution online. That was another Piazza post. My solution. Your solution could be completely different, but at least mine gives you the right output and will work. But what I've done is I actually wrote the solution and then commented out the part. This is the font's a little small, sorry. Commented out the part that talks about looking for the friend list being null. And if you run this in its current form, what will happen is it launches it, and it makes it, and then it ends up saying, it's kind of hard to, it's kind of easy to miss this thing, but sometimes it says terminated. And if your program is terminated, what that means is Eclipse said you did not finish the program with an exit properly of some sort, right? It could have been a seg fault. It could have been some other error that destroyed your program before it could get done. That's what would happen if you forgot to check for the friend list being null. OK, that's one of the things. And if you're looking at that and you're going, let's say you didn't know that, you could say, wait a minute. I want to go look through my program and see if there's something that I can look at the state of it and see. Maybe that'll give me some more information about what's going on here and why the program's terminating. Okay? Here's how you would do it. You go into Eclipse to some line in your program, and let's say so above this I have the part that says find the pirate ID. But let's say I'm pretty sure that's working properly. But I'm not sure about this part here. What I can do is double click on the little line number there, and it puts a dot here, which is tough to see. I showed you this the other day a little bit. Tough to see the little dot, but it puts the dot there. And then if you go to the little debug window, the little debug command, you click debug, and it will ask you, it will recompile it if it has to, and then it will bring up a little window that says, hey, do you want to go into the debug perspective? And you're going to want to click yes. Remember my decision. Don't worry about some errors down here. It generally won't matter. And then you'll go into a different window that actually is the debug window. Okay, and it seems to be taking its time here. But it'll go into a different window that's the debug window that looks like this. And it will start to run your program. And it will go, actually, it'll go to the first line and stop on that line and say, what do you want to do? Right? And you, from there, happens to be the first line, it will say, oh, you'll say, oh, I want to keep going until you get to that breakpoint, which is this little one up here. It looks like a little continue button. Right? If you click on that, that takes you to where you put that. Oops, I've had a different one in here. Hang on. I think this is from before, I believe. Let's see. OK, I'm going to keep going. Let's hope there aren't too many more that I missed. Yep, here it is. OK, so it gets to what happens is it gets to the line that you ended on, or that you put the little. Oh, you can't see it over there. I've been talking about all this stuff. You can't even see it. Hang on. There's a little. Maybe that's a little better. It's tough to see in the lighting in the room. But anyway, point is that it gets to that line that you told it to stop on, and it says, what do you want to do? I've got the entire program state to show you. For instance, if you want to find out what the index is in Hookbook here, you hover over it, right? And it says, hey, the index has a value of 1. Well, that's pretty cool. Like, this is like in your program running. Got a value of 1, right? If you want to find out what the friend count for that is, you hover over it and it says, oh, the friend count is 0. Right? So it tells you all that stuff right there. Okay? And what you can do, you can also, there's actually a little window up here that tells you even more stuff about the program. Okay? If you click on the this, that tells you about that. The this means, hey, this function or this class that you're in. And if you click on that, you'll see, hey, here's my H book with all my pirates in them. Now, here's a little trick. This actually is a pirate pointer. And remember, you've got an array with a pointer that points to the beginning of the array. That's what this pirate pointer for Hookbook is doing. We want to turn that into an array, actually see the array. It's kind of cool. Right-click on this, and it says display as array, which will come up. And you then type the length of the array. Let's say 12. It happens to be 12 in this case. You can make it whatever you want, really. And then it will think for a sec, and then it should, there it is, give you now it's an array. And you can click the little arrow down and see all the different pirates here. Right? And so we happen to be on pirate 1. And if we look at pirate 1, it says, oh, there's the member ID, 1. The name, it's a little tough to get the name, but you can eventually see it if you want. Then it goes down here and it says the friend list here is an int star, which is a pointer to an int array. And what's the value here? It's null. What this means is right now, your friend list for this pirate, right, points to memory address 0, which you're not allowed to do anything with that memory address. You can't dereference it. You can't add things to it. You can't even look at anything. Like, you can't even do a dot operator that uses that. And when you try to do that, your program crashes. Right? So that's the issue with this right here. And you go, oh, that means that if my friend list happens to be null, I'd better deal with that. Okay? So this is, I'm not necessarily expecting you to have been able to do that kind of debugging. But this is one thing that you can do. You can go through the thing and see each little part, okay, and see exactly what your program state is at any one point. Okay, questions on that? I know that was a lot, like real quickly, but you can kind of see how debugging is like possible on this and actually kind of easy in terms of having all the information there that you want. Okay? And it's a little better than putting a bunch of C out statements and saying, here's C errors and C out statements that, you kind of don't necessarily know what's going on there. All right, questions on that? So what I could do is I could go, oh, this is, I could stop this and then go back and say, let me fix the hook book, let me fix this, and I check for the null case, which I already did, but I commented it out, and then I'll uncomment this and then run it again. And when I run it again, sometimes it asks me to save it, but then it should recompile it. It's going to take its little time, and then run it again, and hopefully at this point it will print out the correct results. There we go. OK? So you see how you can use the tools to debug that, all right, with Eclipse? Hopefully a little easier than C outs, C errors. Questions on that or anything else related to Eclipse at this point? OK. Raise your hands if you think you will be using Eclipse after the lab, like since going forward. Most people. OK. All right. That's what I hoped. Again, you don't have to, but I hoped most of you would. All right. Let's go into, actually, I forgot. I'm going to show you the little obfuscated C. I wonder if this has, oh, it should have the ability to do this. Hang on a sec. HDMI. I have no idea how loud this is going to be, or if the speakers even work. But if the speakers work, oh, it was on absolutely the highest level, so hold on. We almost blew our ears out this morning when I showed this. OK, this, remember I said that your program should not be obfuscated? In other words, they should look like real, like they should be readable code. Can you see? I'll blow this up a little bit. This little thing on the left here is actually a program. Now, it spells out fluid in giant letters, but you can see on here that it says things like pound include stdio.h, pound define, right? Over here somewhere, there's a int main. This is an actual program that you can run, like you can compile with the compiler, right? You would have no idea what it does, right, by looking at this. This is why it's an obfuscated thing, right? You have no idea what this does. And that's kind of the point of this little contest that they give, OK? Because people can write this kind of craziness into a program. What's really neat is when you see it actually run, OK? So, there we go. OK. What's happening here is this person is compiling the program and compiling the actual code. You can download this and do it yourself, right? And they're going to compile it, and then they're going to, well, you missed it. Sorry. Let me go back one sec. They compiled it, and then they said, they ran the program, and then they input the file itself into the programs. They ran the program on the code for the program. OK? And you can see what it just did a little bit. But what it ends up doing is it does a fluid modeling like demonstration on the text of the program, right? The guy wrote a fluid modeling simulation that will take the input of his program and model it as a fluid. And he wrote it in this much code, 1 page of code, right? Amazing. Now, he also you can have the column.txt, which is another file, pipe that into the program, and it's another little nice little fluid thing, right? And he built all of these. Supposedly, I think I read something where he said, yeah, I spent a lot of time on this. I don't think my wife's ever going to talk to me again. Right? Because he did this. But some of these are really kind of fun. Pour out's kind of neat. Okay. Whee. Right? And I mean, honestly, he just had to, like, in reality, he had to just figure out the modeling for a fluid and write it into code so that it does this for the text, which is pretty darn neat, right? There's another one that's neat too. Oh, this is a cool one. It's kind of the same idea. Yeah. Right. This guy won the competition, as you can imagine, that year, a couple years ago. Right. Although the other ones, there are a lot of other ones which are really cool too. But, let's see. There's one more that's neat. Clock. This one's neat too. It's like a little hourglass. Yeah. It's got a couple bugs in there, but give them a break. So anyway, so that's that. He also, let's see, his last little thing that he said would that kind of won, that like absolutely won the contest, was he did final program that does it in color. Right? So, the colors mean anything? Yeah. I don't know. I tell you, they mean that this guy's an amazing programmer. That's what they mean. I don't know. I mean, you know, as far as what they mean, I'm not sure. But maybe it's depth. I don't know. So. There we go. So pretty cool, right? Don't make your code look like that. Do as I say, not as I do. Let's see. Oh, there's one other one which is kind of fun. There's this guy who built this one. And this program on the, you can kind of see it up here. It looks a little bit like a flag, right? Anybody? So you guys know I'm in the Navy, right? And have you ever seen those like old movies where the guys on the ships are using the signal flags to like signal between ships in like World War II, right? They still train people to do that. Right? It's kind of neat. I mean, you got one guy with binoculars and the other guy's doing the signal flags, and it's a way to pass information back and forth. And guess what? It doesn't use radio waves. Well, it uses light waves, I guess, but it doesn't use radio waves, so ships a ways away can't see you signaling. I mean, it's kind of clever. But anyway, these are the various the ways you do the flag, right? A Y is something like that or something, right? And this guy wrote this little program. It looks like that. When you compile it, let me see. When you compile it, it looks like, there it is. Okay, you can type something like this. You can say Tufts, and it prints out, right? A little like ASCII art guy going T-U-F-T-S, right? And then he does, I'm done with the word. So kind of cool. You can do anything. You know, you can do any word you want. Word you want, right? And it does the whole thing like that, right? Anyone know what he won the competition for, the category? Best use of flags, right? So yeah, you know, I think they probably made up the category after he got done. Okay, so anyway, obfuscated C. Don't make your programs like that. But if you do want to get into like super duper hacking, you can do that and have fun with it, and your wife will never talk to you again. Okay. All right, let's get into the meat of this lesson here. So the big question, and this is going to be the big question in this class the whole semester, is going to be how do you go about analyzing a program so that you can compare it to some other program? Okay, you have to be able to do that, right? And I'm going to give you an example here, and we're going to analyze this little program. So this program is called ArrayMax. And take a second to look, take like 30 seconds to look through this. And I'm going to ask you if you can figure out what this program does. Okay? Okay, who has an idea what this does? Yeah?
So it finds like the largest, it sets a value for the largest value in the array, and then
Yep.
it goes through every element of the array and finds if the current value is less or greater than another value in the array, and then it sets that to the largest value.
Okay, say the same thing in 7 words.
Finds the largest value in the array.
There you go, finds the largest value in the array. That's exactly right. Okay, so this program just, and by the way, I mean, I named it ArrayMax, right? So, you know, you probably, you know, could use that as some information. But what we're going to do is we're going to analyze this program, and we're going to see what happens. Like, we're going to go through and say, okay, how does this program behave? And how does this program behave in the long term? If we kept increasing n and made a bigger and bigger and bigger and bigger array, how does this program actually behave? Okay? One thing we could do, okay, we could code it up, which we just did, and then we could determine for every instruction of the compiled program the time it takes. We're going to want to compare time. I said on day 1 that time is an important part of this. We could compare every little instruction, and if we really wanted to do it right, we would go to the assembly language, which means your program gets compiled into a language that the computer almost understands. It actually goes farther into machine code, but for all intents and purposes, assembly language is close enough. You could look at all the assembly language instructions and say, how long does this take, and then do that, right? You can determine the number of times that each of those instructions is executed, add them all up, and get a time, right? We could do that. All right, if we tried to do that, well, first of all, this is what the assembly language program looks like. Okay, I don't know if you can see that. Let me boost up the size a little bit here, right? This is what the assembly language program looks like. If you think C++ is hard to read, go try to read assembly code. Your eyes will bleed after like 10 minutes, right? A lot of people do still program in assembly code. And if you ever want to get to low-level programming, I'm sure some of you guys in here have probably seen a fair amount of assembly code before. But my opinion is, unless you really do want to delve deep, 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 try to avoid too much assembly code. In Comp 40, you will see more assembly code. And not too much, but you'll see enough that your eyes will bleed a little. But don't worry about that. Anyway, the point is, we don't want to go into this level of detail, especially not for this class. Okay, we don't want to get, it's going to take too long. You don't even know assembly right now, so it's not worthwhile. And it's really not worthwhile. And you'll see when we get to the end, you'll see why it wouldn't have been worthwhile to do that. OK, that is an option. OK, we could do that. Wouldn't be that great of an idea. Assembly code takes practice to learn, and really we would be overdoing it. OK, instead, here's what we do. OK, we decide we're going to simplify it, at least on the first approximation, to the following. We're going to define a bunch of primitive operations. And primitive means we're going to say that that operation takes 1. And you say 1 what? And I say 1 anything. OK? It's going to be a generic comparison. It's going to take 1 time step, whatever that means. OK? How fast is your computer right now? How many gigahertz is your computer? Any ideas? Roughly, what's yours, Max? What is it? 1.7 gigahertz? OK, mine's actually, I think, like 2.3 gigahertz or whatever. If yours is 1.7 gigahertz, my first computer, when I first got a computer in like high school, it was 4.77 megahertz, right? It was kind of slow compared to now. It's like 1,000 times slower than the computers you might have now, right? Or at least 700 or 800 times slower, right? I don't want to analyze our programs so that the analysis is different if I run the program on my 1986 IBM PC or run it on like the latest 2014 Intel Core i7 or whatever, right? I don't want the analysis to change over time. Okay, because 5 years from now, we're going to have a 4 gigahertz computer or whatever. Lots of other issues involved with that, too. But I don't want the analysis to be different. So what I'm going to say is these primitive operations that we're calling them are going to be 1 operation each. Okay, assigning a value to a variable. If you say x equals 2, we're going to say that counts as 1. Okay, if you say call a function, we're going to say that takes 1. Now, does calling a function really take 1 step? No, right? It takes lots and lots of steps. You have to save a bunch of state. You have to change a lot of variables and things. And it takes a lot of time. But as far as we're concerned, as long as the program isn't meaningful to the algorithm, as long as the function isn't meaningful to the algorithm, 1 step. OK? We're just going to make it real generic. Any arithmetic, add a couple numbers together, 1 step. When you're doing addition, does it take longer or shorter than the time to do multiplication? Shorter, right? I mean, addition's easy. Multiplication, you have to many, many steps. They're the same, and as far as we're concerned, 1, right? To do both of those. Division, the same thing. Comparing 2 numbers, A equals B, 1 step. Indexing into an array. If you say x bracket 4, 1 step. Okay? 1 time step. And returning from a function, 1 time step. Okay? Do you get the idea for the basic ones? And we can argue about what constitutes a primitive operation, but I will give you the argument. If you say, oh, that's actually 2, I'll say, fine. I don't really care. Right? I mean, the thing is, we're going to compartmentalize these. We're going to generally say it's 1. If you want to argue that it's 2 or 3, it's not actually going to matter in the big picture. And you'll see why in a second. Okay? So let's go back to our array max, and let's start looking through this. Okay? The first line up there, the one after the actual function declaration, int current max. I'm going to say that this line is executed once in this function, and it's 2 operations. What are the two operations that I might count in this case? Somebody in the back, yeah. Declaring and assigning. Close. The assigning I will buy. I'm not sure I agree with the declaring, but it's not from fault of your own. It's because you might not know how a compiler does things. But I would accept that. If you told me that, I would accept it just fine, right? Yeah, what do you think?
Accessing the array.
Yes, assigning from an array, like doing the array dereferencing there. That part is the one that I would have counted. So I would have counted the equals, like the setting it equal, and then the dereferencing of the array. Now, why wouldn't I count this? It turns out that compilers, when they set up a function, they actually do that before you call the function. What happens is this gets set up in advance, like the memory is set aside for that. So that's the only reason there. But if you had said 3, I'd be like, fine, 3 is fine, right? But we're going to go with 2 for now. Okay? Let's go to the for loop here. The for loop, okay, the first part of the for loop, a for loop gets executed, like the top line, some of it gets executed every time, right? But something that doesn't is that the initialization of this, the setting of I equal to 1, that only gets done once, okay? That happens at the top of your loop and then never again, right? So that's once during the function running, okay? How about the I is less than n? How many? I'm saying that's n times. Anybody want to argue that with me? Go ahead if you want. We had a good argument earlier in class. Why is it n times and not like n plus 1 times? Any ideas? Maybe I should just let you think about it. Al? Sorry, Max?
I guess that because A, you're skipping the 0th element, and B, you check at the end when looping again.
Yeah, you skip the 0 element. We're actually starting with 1. And then you do check at the end to make sure that you have met your condition. And if you meet the condition, you skip the rest of this. That's how a for loop actually works, kind of under the covers. So good. But anyway, n times for this part. OK, and then the I++. How many times does that get executed? Any ideas? N minus 1, actually, because that one doesn't get incremented on the last time. So this is like kind of in-depth analysis. We're gonna deal. You will not necessarily have to do too much of this. I might ask you like one question on the midterm where I ask you to go through this, and again, I will accept lots of answers for this. You know, if you said this was n and this was n, I'm not going to say, oh, that's off by 1. It just doesn't matter, right? Matt, question?
It was about the increment.
Yeah.
So,
Is increment 1? Is that your question?
yeah.
Yeah, we're going to call increment 1. Is it really 3? Sure. Or is it 2? Sure. Is I equals I plus 1? Is it 2? Yeah, I don't really care. Call it 1 or call it 2. I'm going to call it 1 because it looks like 1. It's one thing. Right? We're going to be a little loosey-goosey with that. OK? All right. Anyway, any other concerns about this one? If you add those things up, it's 2 times n minus 1 operations. OK? If you add all those up for the loop. OK. Next. Current max is less than a bracket I. Do we have to check every single element before we get to the maximum? Like, do we have to, if let's say we have an array, we don't know anything about the array except that it's got elements in it, and we're going down the list looking for the maximum. If the maximum is a third of the way down the list, can we stop? Why not? Because what? It could be in the end. You don't know yet, right? You don't know anything. Now, when could we stop? What kind of array would we have to know that we can stop? Sorted array, right? Yeah, if it's already sorted, well, then we would just go to the end, right? If it's sorted, or at the beginning, or however we're sorted. But yeah, if we know more information, then we can do that. OK? If we know more information, then we can do that. OK, how many times does current max equal AI get executed? We don't know, right? If you've got a list of 10 integers, and this one's 1,000,000, and all the rest are below 7, well, you hit the first thing you do is you say, the current max is the first one, and it's 1,000,000. And then you look through all the other ones, and you never do this, right? What if that 1,000,000 happens to be, what if it happens to be a completely sorted array? 1, 2, 3, 4, 5, 6. How many times do we do this one? Every time that we look at this, right? So n minus 1, right? That makes sense? we go through this loop, and the only times we execute this line is if the maximum is less than the current max, and if it's a sorted array, it's going to be every time. If it's sorted, higher one on the end, right? So this is a case where we've got at most n minus 1 times, and at least how many times? What's the least number of times this gets? 0. If it's the first one, if we already have the maximum, you never reset the maximum. OK? So this is a range. Well, we'll have to look at the range. OK? OK, and then how many times do we execute the return statement? Once, right? So there's one more operation. OK? Oh, I didn't even say that the loop total, if you add up all the totals here, it's just 4 times n minus 1 is the minimum, and 6 times n minus 1 is the maximum. OK? That's all that is. All right, and then once here. OK, so we've gone through this kind of excruciating thing here where we look at all this. And then we look at the, and then we add these all up. All right, easy enough to do if you've written it all down. Add them all up, and here's what you get. The array max function has at least, add all these up, 5n operations. And n being the length of the array, remember, right? And at most, it goes all the way up to 7n minus 2 operations. OK? All right, so we've said, great. Now we know the minimums and maximums, right? What this really means is that the best case is we can do this in 5n if the maximum was the first value. The worst case is if they're all in order, and we have to change it every single time, and that's 7n minus 2. OK? What's the average case? What is it? 6n minus 1. Who knows? It totally depends on what? Depends on your data, right? Depends on your data set, right? For this, you can't really give an average, right? I mean, you can do some empirical testing and have lots of different types of data and say if the data is random, the average is going to be blah, blah, blah. And if the data is, and this, and you can do some of that testing. We are not going to worry about that in here. If you love this kind of stuff, you're going to see a lot of it in algorithms class, possibly in theory of computation class, right? But you will get into some of the details here. I won't ask you about the average case. I would almost never ask you about the average case, especially in one where it would be an empirical sort of thing where you have to do the tests to figure out based on your types of data. OK? All right, so that's the basic kind of analysis. If we wanted to do that level of analysis, we can. And you may do some of that in some other classes like algorithms class, right? The big question is, do we really need that much detail? Do we need that much detail? We don't, right? That much detail is actually too much for our purposes, OK? If you're in the nitty-gritty of, you're trying to design something like Facebook, and you want to know if this algorithm is better than this one, they look roughly the same, yeah, you might want to go into some of this analysis. For our purposes, we'll never really have to do that. We're going to simplify it. We want what is a big picture approach. And here's the big picture approach for array max. Array max actually grows proportionately to n, regardless of what the order of the arrays are. In the long term, if it takes 1 second to do 5 elements, it's going to take 10 seconds to do 50 elements. OK, does that make sense? As you grow, it's going to end up behaving like that. OK, we'll get into a couple more details about that. All right, but in the broad spectrum, we're going to end up doing doing the analysis such that we end up getting this instead of going through all that counting. OK, I showed you the counting to show you kind of how you can think about it. But as it turns out, you're going to start seeing these and not even having to do any of this counting. It's going to be good. So all that scaring I did a minute ago, don't need to worry about it. OK? All right. We are going to do this thing called big O notation. OK? We also call it asymptotic analysis. Big O notation, OK, is a simplification. Mathematicians use it. You'll see it in discrete math. You'll see it in algorithms class. You'll see it in theory of computation, et cetera. What it is, it's a mathematical way to say, let's simplify the algorithm down to its bare minimum idea long term. OK? We call it big O notation. You can think of O as in on the order of. And what I mean by that is it's on the order of a linear operation. Linear being If it takes 5, if you've got 5 times as many elements in the array, you're going to have 5 times slower performance. Okay? We're also going to talk about things like logarithmic. We're going to talk about something having an order that's logarithmic, exponential, cubic, quadratic. We'll get into all those in a few minutes. Okay? Here's what Wikipedia says for big O notation. Big O notation describes the limiting behavior, very key phrase right there, limiting behavior of a function when the argument tends towards a particular value or infinity. Aha, or infinity. Usually in terms of simpler functions. In other words, if you make this not a problem of 100 elements in your array, but 1,000,000 or 1,000,000,000, how does the program behave? Okay, that's what we're looking at, like that level of understanding. Okay? If you are not a mathy person, you might want to hide your eyes for this next slide. Okay? This next slide is actually it's kind of a mathy slide. I wanted to show it because some of you guys might like it, and if you want, you can get more details in other things. But here's the slide. Okay? What this is describing is our function, or our algorithm that we're worried about, is f of n here. Okay? We're going to compare it to another simple function. Okay? G of n, although this doesn't look simple, g of n is going to be a simple function, okay, in general. And what we're going to do is we're going to say, at what point does g of n become bigger than f of n? It's actually not at what point, but at some point, the function that we're trying to compare against will become slower than our function forever. Notice here at the beginning, f of n is actually slower than the other function at the beginning, right? What's going on there is, if you only have 10 elements in your array, that's when the setup for the for loop, the return statement, right? The other little things that I said, oh, it's either 1 or 2 or whatever, that's when that starts to make a difference. If you have an array that's only 5 elements long, all the other stuff at the beginning, setup and all that, is actually going to start to matter. And so what that means is you can't worry about the little parts of this. Like, asymptotic analysis does not work for tiny little arrays and for tiny little pieces of code, like code that does not have many, many elements in it. We're talking about long-term behavior here. Okay? Long-term behavior, there's some function that we're going to say that f of n is on the order of the other function because it always stays lower than that function forever. Okay? There may be many functions that this fits into. We're going to try to find the one that's closest to f of n. Okay? Now again, the details of this slide, you are not going to need to know this. I just wanted to kind of give you a feel for what we're talking about here. Okay? All right. What does that actually mean? Or what's the bottom line on all this? There's a dirty little trick. Okay? What you're going to do is you're going to look at the number of steps you calculated, if you end up doing all that calculation. And you're going to find the ones that are the biggest contributing factors to that algorithm or array, or algorithm or function. And then that's going to be your answer. So what's more important, 2 or n times of things? Like, in other words, if you have 2 things you have to do, 2 steps, versus n steps, if n is huge, what's going to matter more, the 2 or the n? The n is going to matter more, right? The n is the only thing we actually care about in this. We actually don't care about any constants in here. Turns out that anytime you have a constant, get rid of it, right? For this analysis. Later in other classes, you won't get rid of it. But in here, you're going to get rid of it. So 7n minus 2, at some point in those 2 functions, there's another function that's like basically n, that 7n minus 2 is always going to be less than. Or I should say, well, sorry, it's the other way. Actually, the other way around. It's actually going to be slower than the other one always. Okay? Did I say that right? I think I got that backwards. But anyway, the point is, you're going to have to just get rid of the constants and take the biggest factor out. I'll show you another example in a second here. Before I get to that one, here's the ones we're going to care about in this class. We're going to care about constant factors, or constant we're going to care about being on the order of a constant function. What does that mean? That means that if I had an array of 1,000 elements, it would take one time step to do whatever I'm doing with them. If I had an array of 1,000,000 elements, it would still take one time step. In other words, the number of elements does not matter anymore. Okay, that's what constant is. This is the holy grail of algorithms. If you can find an algorithm that gives you constant whatever for your function, that's the one you're going to go with. Remember when on day one I said I talked about, I gave those 4 different comparisons between different lists. Remember which one was like amazingly fast? Hash table? Yeah, the hash table. That's a constant data structure. Like it behaves like with constant time, which is why it's used for like all these different things. Because a hash table is really great. There's some overhead to it when you set it up and things, but in the end, that's what makes it like run really fast. Okay? We've also got logarithmic behavior. Okay? Anytime you are breaking a problem into half, and then half again, and then half again, and then half again, and then half again, that's logarithmic behavior. Okay? Those problems tend to get very small very fast. This is why you can play think of a number between 1 and 1,000 game and not go crazy, because you can actually narrow it down very quickly, right? You could play the game, think of a number between 1 and 1,000,000,000, and it takes log base 2 of 1,000,000, which I don't know what that is. Let's see, log base 2 of 1,000,000, 2 to the 20th, I believe, is 1,000,000. So if you think of a number between 1 and 1,000,000, and you're clever about always doing half between what the guess is and which direction you're going, you can do it in 20 guesses or less, right? Because that's how fast logarithmic is. Logarithmic is great. If you can't reach constant, go for logarithmic. Sometimes you can't do this either, right? But that's the one to do, the one you want to shoot for. Linear is the one we just talked about, right? If the number of things that you have to do is directly proportional to how long it takes to do that, that's a linear behavior. Okay? 10 times more elements, 10 times slower. That's linear. Okay? Quadratic is when you have like n squared behavior. If you do 10, if you have 100 items, right, and it takes some amount of time, and then you have 1,000 items, it's going to take 100 times more time. In other words, it's going to take 10 squared more time. Okay? We'll go into more details about that. Quadratic functions come up a lot in programming. Okay, anybody have any idea where you see a lot of quadratic functions? What do you think, Cecily? A for loop within a for loop is a good example. There are specific examples of where you see for loops within a for loop that it becomes really apparent. Did you have a comment? Anything that works with matrices, or for that matter, anything that works with a screen, right? Like your display up here. If you want to look through all the pixels on your display, you start at the top left and you go all the way this way, and then you go back and you go all the way this way on the next line down, and then you go all the way this way. Isn't that, if this was a square, wouldn't it be n by n? Right? That's quadratic behavior. This is the reason that you guys have fancy GPUs in your computers, right? Because of this exact problem. Quadratic behavior is slow. Quadratic behavior is slow enough that when you want to deal with a lot of graphics, it really taxes your processor. So smart people have said, oh, let's rethink the problem of this quadratic behavior, and let's come up with graphics cards that do deal with that. Okay? Graphics cards actually have many processors. Okay? If this room was a graphics card, each seat would be a processor, and each seat would be working on 1 pixel in the screen. Okay? They've parallelized the problem. They've said, oh, we've got an issue with this n squared behavior, and they've figured out a way to deal with it so that you can have fun, games that are really fast in your graphics and so forth. Okay? Fine. The next one would be just general polynomials. Quadratic, then you go after quadratic, n cubed, which is cubic, right? Is there anything that we might want to program that has a cubic type behavior? How about all of real life, right? If you want to model the real life, are you going to say model real life? 3D simulations? Yeah, anything 3-dimensional. This way, and this way, all of a sudden you're into cubic behavior. That's why some of this three-dimensional simulations are really tough, They're really tough because cubic behavior is slow, and so you need really fast processors or you need to rethink the problem. Okay? So that's polynomial. Exponential. This is where you've got some constant that's raised to the nth power. If you ever find yourself writing exponential functions, stop and say, am I sure I'm doing this right? Because the odds are very good that you can do it better. And if you try to do something in an exponential fashion, you will fail. Or your program will take a long, long, long time to run. Okay? Anybody ever played the game Tower of Hanoi? So let me show it to you. Oh, I have to take out the trash when I get home. Let me open this up and show you. This is what the Tower of Hanoi game looks like. Okay, it's this little game, right? Have you ever played this where you have to move the disks from one position to from position 0 to position 2 over here? And you have to figure it out. Well, the rules of the game are you can only move one disk at a time, and you can't put a bigger disk on top of a smaller disk, right? So watch what happens. OK, count the number of steps. I think it counts for me. I think I'm going to do this. I always screw this up, so I may get wrong. OK, 1. OK, and then this one might go here, 2. And oh, it's got sound. And 3, right? And then 4. And then I don't want to move this one over here. I want to move it back over here. 5, 6, and 7. And I win, right? OK, so that's with 3. It took, for a disk size of 3, it took 7 steps. For a disk size of 4, OK, anyone know how many steps it's going to take? Any guesses? 15. Who said that? Yeah, I like that. OK, it doesn't say that up there, does it? That's great. It actually does take 15 steps. OK, I'm not going to go through them because I'm so terrible at this game I would screw it up and you'd laugh at me. But anyway, the point is I probably already screwed it up. But anyway, it's going to go through all these and you're going to have to move back and forth. And like this one, you have to move this one on here before you can move this one off here, et cetera, et cetera. And this is an exponential problem, right? What's cool about this little thing is that it'll actually solve it for you. And so we'll watch. 1, 2, 3, 4, 5, 6, and then you can do something cool where you go fast forward, right? And it does it. So it takes, right? Takes 15 steps to do this, right? Well, so as it turns out, it's 2 raised to the number of disks minus 1. So if there's 3 disks, 2 to the 3rd is 8 minus 1 is 7. 7 moves. 4 disks, 2 to the 4th is 16 minus 1 is 15. 15 moves, right? With 5 disks, what would it be? 31, because 2 to the 5th is 32 minus 1 is 5, right? What would it be for, this goes all the way up to 8 disks. Any idea? 2 to the 8th is 256, I believe. 256 minus 1 is 255, so it should take 255 ones, right? And we could have it sit here and go, right? And then do it, and then, one at a time, and it's got to do that one there. There's an algorithm to do this, by the way, but the algorithm happens to be exponential, right? And I could let it, right? But I'm not going to do that. I'm not going to make you sit through all that. Go do it on your own. I know. You want to watch the fancy things, right? But it's hard, right? And it's harder. And 8 is 256. 9 would be, or 255, and 9 would be 511. And 10, you're only up to 10 disks, and you're at 1,000 moves, right? With only 10 disks. This is why these exponential functions are not a good way to go about business. If you can't, Tower of Hanoi doesn't have a solution that's not exponential, so you're stuck. But many other things that you want to do don't have exponential solutions. OK? All right, questions on that? All right, you will get very used to seeing all these types of behavior in class. OK? All right, back to the dirty little trick. Our dirty little trick here is, again, look at the number of steps you calculated, throw out all the constants, find the biggest factor, and that's your answer. OK? It's really kind of cool when it comes down to it. All right, all this analysis we're doing, you throw out most of the stuff that you're looking at because you do it. What's more important in this case, the 5 or the n cubed? N cubed, right? What's more important? This is a tricky one. N times log n. Is that better or worse than n cubed? It's actually better than n cubed. It's like faster than n cubed because n times n would be n squared, and n times log n, which is actually better than n, is even better than better than n squared. So it turns out that these two things get canceled out. We don't worry about the constants. The 20 goes away. So this whole function is order n cubed. Okay? It kind of reminds me of significant figures a little bit. Right? You guys have all done significant digits in like science class and things, which actually brings up my best nerdy joke, which is, so two guys walk into the Museum of Science, right? They walk into the Museum of Science. You know there's a big dinosaur skeleton there, right? The one guy turns to his buddy and says, see that skeleton over there? That skeleton's 1,000,004 years old. And the other guy goes, how do you know it's 1,000,004 years old? And he says, well, I came here 4 years ago, and they told me it was 1,000,000 years old. Right? No, it's not 1,000,000 years old. It's not 1,000,004 years old. It'll be 1,000,000 years old for another 500,000 years. Right? I mean, that's the scale. Like the significant digits is what we're talking. Very similar idea here. Okay? All of this boils down to the thing that's important, the n cubed part of it. Okay? Long term, these other terms drop out. They don't even matter anymore. Okay? All right. Now, let's go back to what Cecily was talking about. Nested loops here. Okay? Nested loops, a for loop inside a for loop. Right? Yo, dog, I heard you liked for loops, so I put a for loop in your for loop. Right? All right? So you got a for loop inside the other for loop, and you're running this. So let's look at this. For the first for loop, how many times did we say this like part of the loop ran? We said it was like n minus 1 times 2. N times, right? Don't worry. This part, if we said this was a primitive sort of thing, this end runs n times. And how many times does this inner part loop run? It runs n times for every loop outside, right? That ends up being n squared behavior. And so this is why we've got a quadratic function here, okay? The inner one, n times. The outer one, n times. The inner one goes every time the outer one goes, so that's why it's n squared behavior. Okay? Cubic, we already kind of talked about that. 3 loops, same thing. N cubed behavior, because you've got a loop inside a loop inside a loop, right? If you're doing 3D modeling, you see a lot of this stuff. They try to make it so that it runs efficiently if you can. Okay, but it's slow. N cubed is slow behavior. Okay. All right. Let's look at searching. Searching's an interesting one. Okay, take a look. Take a couple seconds to look through this code. There's a lot of code up there, but just take a look at it and see if you can figure out what it's doing. This one's assuming that these are. I believe this is assuming that this is in an ordered array, but in the big picture it doesn't really matter. What's going on here? Anybody tell what's happening here? I mean, we're calling it search array, so what's it doing, John?
You're inputting a number to find, and you just go through and move through the array, compare every number to number to find. If you find it, break, and if you don't find it, you just don't find it, you break the loop.
Yeah. What's the best case here? Like, how long is it going to take? If it's the first number, it's going to take 1, right? Basically, I mean, it's going to take 1 times however many things in here, right? Well, till there. It's going to take 1, and it's going to break out of this, so you're going to find it. What's the worst case? Yeah.
It's not in the array, but it's bigger than the largest number.
Not in the array and bigger than the largest number. You got to look through all of them, right? So if we want to compare the best case, the order of the best case, what's it going to be? Oh, what? Let's go back and look at the choices again. If you find it instantly, which one of these is it going to be? O1, right? That's the best case for this, just the best case, right? If we have to go through every element and look, which one's it going to be? Order n. Notice we didn't have to do all that fancy like counting. We actually didn't do that in this case, because we can just look at them and go, oh, is it going to go through every element? Yes, it is. Therefore, it's going to be order n. Does it only go through one element because it's the first one? Then it's going to be order 1. So this is an algorithm that, again, has minimums and maximums. There we go. Okay, minimums and maximums. Best case, order 1. Worst case, order n. Okay. Many times in this class, we will actually care about the worst case. Okay, the best case, if you're sorting something, we're going to talk about sorting in a couple months, right? We're talking about sorting things. If your list is already sorted just because it comes to you sorted, in general, most of your algorithms, not all of them, most of your algorithms will be able to run very quickly, and that's the best case. But we don't care about that best case, right? We care about the worst case in a lot of times. Many times for sorting, we care about the average case, because for some sorting algorithms, the worst case is bad, but the average is good. I won't make you calculate averages, okay? But those are the kinds of things we need to think about. Best and worst, mainly the worst. Okay? All right, let's look at binary searching. All right, this one's a little trickier to understand here. Okay, but basically, this is playing the what's my number game. Okay, it's basically playing the what's my number game. We know that the array is sorted, and we're playing the what's my number by halving the array each time. We're going through and we're saying if the last minus first is less than 2, return the one that we found. Let's see, this is actually a little bit confusing here. I probably could rewrite this, but basically this is the key line in here. We're basically changing this by a factor of 2. And by the way, the logarithmic base that we're going to be using is 2. Okay? And I also just gave away what the behavior is. But it's log n behavior because every time you divide by 2 through the problem. So you cut it in half and half and half. If for some reason you were able to divide the problem in thirds, it would be logarithmic as well, just a logarithmic of base 3. Not going to worry about that. Okay? Not going to worry about that. All right, questions on this one? This is if you're ever breaking things into halves each time, you will see lots of logarithmic behavior. Okay? All right, so here's a couple numbers on this. If we have an algorithm that has 1,000 elements, and the logarithmic version, let's say we have this algorithm, we've coded it in a whole bunch of different ways. Coded it in the constant way somehow, coded it in logarithmic somehow. Let's just say that we could do this for some algorithm. I've never found one that you can actually do all these in this way, but let's just say you could. If the logarithmic one took 10 nanoseconds, by the way, that's really, really fast. Okay, 10 nanoseconds is super duper fast. Okay, you guys know who Grace Hopper is? Anybody ever heard of Grace Hopper? You guys have heard of Grace Hopper, right? Who is Grace Hopper? You know, who is she, or who was she? Do you have any idea? She was a programmer. She was actually one of the first computer scientists, like when computer science became a field back in like the 1950s. She designed the programming language COBOL, right? Super brilliant woman. She was actually in the Navy. She became a rear admiral in the Navy, like super high up in the Navy. And she was kind of a nerd, but she was really like smart and did lots of computer stuff, right? If you ever want to see anything about her, go watch a video. Go on Google and type in Grace Hopper, David Letterman. And she was on David Letterman in like her 80s, right? And she just, it's a really fun interview. But anyway, there's a big conference every year. I'm actually going to miss a class here to go to it in Phoenix in October. It's the Grace Hopper Conference. Hopefully some of you guys will get to go to it, particularly the females. It's a females in computing conference. So it's pretty cool. But anyway, Grace Hopper used to carry around, and she talks about this in her little David Letterman thing. She used to carry around a piece of wire that's about this long. And she used to hand them out, like carry a little packet of wires, and she used to hand them out. And she would say, this is a nanosecond. And you go, what are you talking about? That piece of wire is a nanosecond. She goes, no, that's how long it takes light to go from this part of the wire to this part of the wire, right? A nanosecond. It's about this long. And she used that to demonstrate the fact that as computers need to shrink because the speed of light actually makes a difference, right? If you built a computer and the parts were like this far apart, right, you could never get 10 nanoseconds or 1 nanosecond behavior because the speed of light actually limits it. You won't even be able to get 1 nanosecond, right? So anyway, Grace Hopper, go look her up. She's cool. David Letterman's fun. If you had the logarithmic version of this program ran in 10 nanoseconds, the constant version would run 1 nanosecond. Awesome, right? The linear version would run in 1 microsecond, also very fast. As far as you're concerned, 1 microsecond is like super duper fast, right? The quadratic one, a millisecond. Millisecond's not that, not slow, right? A millisecond's pretty fast. So you could do a quadratic algorithm in a millisecond. You don't care about a millisecond. In fact, you could probably do like a polynomial one of some other order. And if it takes 1 second, you're really not going to worry too much about it, right? Although seconds do add up pretty quickly, right? Exponential one here, 284 years, right? Not so great, right? 1,000 elements, 284 years, not so great. What if we changed, instead of 1,000 elements, okay? Instead of 1,000 elements, we still had 1,000 elements, but it took 10 milliseconds instead of 1 millisecond, or 10 nanoseconds? 10 milliseconds for logarithmic, 1 nanosecond, still super fast for the constant. Linear now is 1 second. Not too bad, but not, seconds add up. Quadratic all of a sudden takes 17 minutes. Holy smokes, you go from this one only takes 10 milliseconds, this one takes 17 minutes. Now you're talking about time. You do not want your computer to take 17 minutes when you hit the return key, right? Which is happening to some of you when you're using Eclipse from home, but different story. But you don't want that to happen, right? Polynomial, 700 hours. Whoa, right? You're not going to wait for that. Exponential, heat death of the universe. Okay, you're really never going to be able to wait for the exponential one. It's going to just, in fact, 10 to the 284th years is also the heat death of the universe. But this one, really, you're not going to have the exponential. You're just not going to do it. So keep an eye out for those sorts of functions. Okay? All right. So for a summary here, constant behavior, not dependent on the number of elements, the holy grail of algorithms. If you can get it so that it doesn't matter on how many elements you have, awesome. Linear, at each step you reduce the problem by a constant amount like 1. If you're going through a loop and you're going down by 1 each time, it's probably a linear algorithm. Logarithmic, you're doing the halves, thirds, etc. Quadratic, that's where you're talking about the doubly nested loops, right? Cubic, triply nested, 3-dimensional, all that. And then exponential, here's what's happening with exponential. You're reducing the problem into 2 or more subproblems of smaller size. You are reducing the problem size, but you're making twice as many each time, right? So you get smaller problems, but you've got more problems. So in the end, you can solve it, but it just takes a long, long time. Okay? All right. Let's see. I don't think we'll get a chance to do that. So any questions on algorithmic analysis? Max? What's that? Did you see it already? Yeah. This one is kind of fun, yeah. I'll start with this. I'll start with this on Monday. The next one's the one where you ask for the height in inches, and we'll talk about that. It's a little bit fun. Okay. Other questions on anything class related or otherwise? Yes.
Should I email you if I wasn't able to sign up for the class?
Yeah. If you weren't able to sign up for the class. Oh, most people I think emailed could sign up if you weren't. Fill out an add drop form from the undergraduate school. I will sign it, and we'll get it going.
Okay. If I already put one in that envelope a while back.
I think that's the one they tried to do, but it didn't work for you for some reason.
Fill another one?
Yeah, an actual add drop form.
Okay. And you have, where's the one that you have your, didn't you have a digital one with your signature?
Oh yeah, I'll email it to you. Stop by right after class. I'll email it to you. Okay. Anything else? See you guys Monday.